Morning.
Morning, Joe.
Morning. Can you hear me clearly?
Yes.
Okay.
Yeah, sure.
Okay. Okay, today we'll go through some topics that were brought up last week. And then after that, we will look at the past year paper if we finish this on time.
Okay, sure.
Okay, sure.
We'll just wait for a couple more minutes and then we'll start. Okay, I'm just going to quickly do attendance and then we'll start, okay? CK here?
Yeah, sure.
Daman?
Yes, sure.
Edmund's not here. Diksha? Also, yeah, Diksha won't be here. Kezia? Not here. Justin? James? James, are you here?
Yeah, sure.
Okay. Nikita not here. Moshika?
Yeah, sure.
Cedric? Cedric here? Okay. Desiree?
Sure.
Yong Hong not here. Xenia?
Here, teacher.
Okay. Did I miss out anyone's name? Who is this again? 01116013644. Who is that? Do you all know? The profile picture is the anime character, I think. Who is it again?
My name is Gloria.
Oh, Gloria. Okay. Okay. Okay, let's start. We will start, so some topics that we're going to look at is reflection, refraction, the formulas, conservation of momentum, and half-life. Okay. Okay, let's start. Okay, before that, I just want to go through this one as well. Last week's question on this, the 4 balls with different masses dropped from the heights shown. Taking into consideration that air resistance can be ignored. So we're not taking into consideration air resistance having an effect on these balls, like these balls of different masses. So we want to look at acceleration, okay? We want to look at speed essentially. Okay, so now the first thing we must remember is when we have an object that is in motion, we're looking at the mechanical energy, where the mechanical energy is the addition of the potential and the kinetic energy. And when we're looking at those things, we're also looking at the total energy available for the object as it speeds and changes in position. So in this case, it's changing position, going from the air at the top to the bottom. Okay, and then there is and when it changes from one point to another as it's falling, okay, as it's falling to the ground, it's changing. It's just that it happens really quickly in front of our eyes, but if we were to do a slow-mo of it, we will see it falling really slowly from point to point to point to point before it falls down. Okay, which is why we look at the formula mgh equals to half mv squared. This is what I mentioned last week. Let me see if I can get the formula on the screen. Okay. Can you all see my screen?
Yeah, sure.
Okay, so we are essentially looking at this. Okay, so we have, like I said just now, we have when the object is moving, we have kinetic energy plus the potential energy. And according to the law of conservation of energy, energy cannot be destroyed. It's conserved. The total energy before, total energy after is the same, and usually energy is converted to different forms, but it cannot be destroyed. So in this case, we are equating the kinetic energy to the potential energy, because that is a direct measure of the total energy available to a moving object as its speed and position changes. So we equate these two, mgh and half mv squared. So it will be mgh equals to half mv squared. And in this case, m and m can cancel out. So m is the mass, g is the gravitational acceleration, because we're looking at a free-falling object. In this case, we can take 9.8 or 10. And then h is the height, which changes for each ball. So this one, the height is 1, 2, 3, and 4, respectively. So when we use this formula, mgh equals to half mv squared, taking out the m, you will have gh equals to half v squared. Okay, and then if I were to switch it around, because I want to find for speed, v squared is equals to 2gh, and v is the square root of 2gh. Okay, I'm just going to take a picture of it. And put it on the group in case you didn't get that. Okay, so gh equals to half v squared. So the height will be different, 4, 3, 2, and 1. And just from basic multiplication rules, if let's say if my h is going to be big, it's going to be greater, my velocity was going to be higher, which is why for this question, the height 4 will give me the highest speed. So ball S will have the greatest average speed. Okay, does anyone has any questions on that?
No, sure.
So when we're looking at free-falling objects, we want to remember kinetic energy and potential energy. And then we use the formula mgh equals to half mv squared. Okay. Okay. So that is, okay, that is for last week's question. Okay, and then today we're going to look at, just refreshing on these things. Okay. So very quickly, when we're looking at light, we have reflection and refraction. Reflection essentially means light bouncing off a surface, and then refraction is the bending of light rays when they pass at an angle in or out of material. So we're looking at refraction, we're looking at light ray passing through different mediums essentially. Okay, when it passes through different mediums, the bending of light ray happens. So law of refraction is the Snell's law. The incident and refracted ray are in opposite sides, okay, because it's going through a different medium. Okay, and then we have I for incident angle of incidence and R for angle of refraction. Okay, so the value of sine I over sine R is constant for light passing from one medium to another medium, and that is Snell's law. Okay, and this is what we, the constant is the refractive index. So n is equals to sine I over sine R. I is basically the angle of incidence, R being the angle of refraction. Okay, so let's say I have this. I have a diagram showing a ray of light moving from air to liquid. Find the refractive index. Okay, can you all find the refractive index based on this formula? N equals to sine I over sine R. So what is the refractive index?
N equals sine 30 over sine 45.
Are you sure?
0.71.
You see where the angle of incidence is it's to the normal. It's always go nearer to the normal. So this will be 60. Okay, you must always remember when you're calculating the angle, measuring the angle, it must be towards the normal. Okay, so you have sine 60 divided by sine 45. So what do you get?
1.22.
Yep, 1.22. Okay, so remember, it's always the angle nearest to the normal. Okay, and then we have refractive index. Refractive index of a medium can be defined as the ratio of speed of refracted light in vacuum over speed of light in the medium. So speed of light in vacuum is always the same. It's 3 times 10 to the power. It's always constant. Okay, 3 times 10 to the power of 8, and then speed of light in medium depends on the medium essentially. Okay, so that is, and then to when you divide those, you will get refractive index. Okay, and then we also have real depth and apparent depth when we're looking at refraction from air to water. So real depth of an object is the actual distance from the object to the surface. Okay, so let's say this is the point. The real depth is the actual depth. The apparent depth is what we see. Okay, so when we look at something in the water, it always appears nearer due to the bending of light. So where it appears to us, that is the apparent depth. Okay, the vertical distance of the image of the object from the surface. So the real depth is always larger than the apparent depth. Okay. So another formula for refractive index is real depth divide the apparent depth. Okay. And then we look at refraction from less dense medium to denser medium. Light passing into an optically more denser medium is bent towards the normal. Okay, so when you're going from less dense to denser, the ray is going to bend nearer to the normal. Okay, whereas to from a denser to less dense, it's going to go away from the normal. So the refracted angle of refraction is going to be larger. Okay, so it's bending away from the normal. When the ray is perpendicular to the refraction plane, then there's no refraction. Okay, so some examples of refraction taking place is swimming pool appearing to be shallower than its actual depth, a spoon looking bent in a glass, twinkling of stars, the setting sun looking oval in shape. So these are just examples of refraction. So far, okay? Anyone has any questions?
No, sure.
Yeah. No, teacher.
Okay, then we look at total internal reflection and critical angle. Okay, so if you all remember, total internal reflection happens when, does anyone remember? Why does total internal reflection happen? What causes it?
When the angle of reflection is at 90.
Why does the angle of reflection be at 90? That is not total internal reflection yet. What causes the angle of reflection to come to 90? Look at the diagram. What is happening? This is total internal reflection.
So when you
What
move
has
it to
happened?
the right.
Sorry?
So when
There
you
is
move it to
critical
the
angle.
left.
Sorry, say that again?
When
Move. Oh, sorry. You say first. I just.
you say
So when you move the light source to the left.
Okay, so when I'm moving the light source to the left, what am I doing?
You're changing the angle.
Okay, I'm changing which angle?
The incident ray.
Correct. So I'm changing the angle of incidence. Okay, so from here it's going, I'm moving it to the left, and I have a critical angle. So critical angle is when the angle of reflection is 90 degrees. But when does total internal reflection happen? In reference to the critical angle.
When the angle incident actually critical angle.
Correct. So in terms of the critical angle, in reference to critical angle is when the angle of incidence when the angle of reflection is 90 degrees. But when I move the light ray, when I increase the angle of incidence to be beyond the critical angle, that is when total internal reflection happens. Okay, so if the angle of incidence is greater than the critical angle, then total internal reflection happens. Angle of reflection being 90 degrees is when the angle of incidence is equal to the critical angle. So when I put the light ray such that it is at the critical angle, then I will have reflection of 90 degrees. And then if I move it beyond the critical angle, that's when total internal reflection happens. Okay? And then I have an equation that relates critical angle to the refractive index. Refractive index n is equals to 1 over sine of the critical angle. Okay. Okay, very quickly, requirements for total internal reflection to occur. The light ray must propagate from an optically denser medium to less dense. So when we're looking at total internal reflection, we're looking at light ray going from denser to less dense medium. And the angle of incidence must exceed the critical angle. If it is at the critical angle, it's not total internal reflection yet. It's just 90 degrees to the normal. And then if it exceeds the critical angle, then only total internal reflection can occur. Okay, everyone okay so far?
Yeah, sure.
Sure.
Yeah, okay. Okay, so that is on light. Okay, and next we'll look at conservation of momentum. Okay. Just give me a moment. I will just look for the slides. Okay, next we look at conservation of momentum. Okay, we're looking at what happens when two objects collide. And then we're looking at momentum before and after collision. Okay. So, conservation of momentum basically states that the total momentum of a system before a collision is equal to the total momentum after collision. Okay, similar to my energy, conservation of energy, there's nothing that's going to be lost in a certain way. Everything is conserved basically. Okay, so momentum before collision and momentum after collision they're going to be equal. That is the principle of conservation of momentum. Okay, so let's say we have this example of a moving trolley and then the other trolley is stationary. They both have different mass and they're both moving at different speeds. Of course, the stationary trolley is going to be at 0 because it's not moving. And let's say the condition is they stick together after impact. Okay, so we know that momentum is mass times velocity. So for trolley A, the mass is 0.5 and the velocity is 1.2. So my momentum is 0.6 kg meter per second. For B, the momentum is 0. Why is the momentum 0? Because there is no initial speed. So when you take the mass and you times with the speed, it's equals to 0. Okay, so which means my total momentum before they stick together, before they collide, is going to be 0.6 plus 0, which is 0.6 kilograms meter per second. And according to the law of conservation of momentum, the principle of conservation of momentum must remain the same after the impact. So let's look at after the impact. So the question says, the situation is they stick together after impact. Okay, so the moving trolleys, they're going to get stuck together because they're sticking together. So we know that the total momentum before is 0.6. Now, after they stick together, the mass is going to combine. Okay, it's going to be 0.5 plus 1.5, which is 2 kgs. So velocity is momentum over mass. So my total momentum before is 0.6. My mass is now 2 because they are stuck together. So my velocity is 0.6 divided 0.2, which is 0.3 meter per second. So that's going to be my velocity after collision, after they collide and stick together. Okay? So let's look at an example. Okay, you all try. I have mass and velocity of the child, and then mass of the guy with the velocity. What is the momentum of the rugby player before the impact and the speed of the two together after the impact? Assuming that they are sticking together. So first one, what is the momentum of the rugby player before the impact?
800.
Okay, 800 kilogram meter per second. What is the speed of the two together after the impact?
Is it 5?
How do you get 5?
Because the velocity is 5.
No, you have to take the total momentum. You have to use this concept, because the momentum before is now 800, and then my speed, which in this case is the velocity, is going to be total momentum divided by the total mass. Because now they're going to stick together. So the total momentum before is 800 because the velocity of the child is 0. And then I want to take,
Calculus 20.
sorry?
I got 20.
20? How did you get?
Yeah,
Huh?
got 4.
4. So now the total momentum before collision is 800. Okay, because the child doesn't have momentum because it's 0 velocity. So the total before is 800 plus 0, which is 800. The mass after they collide is going to be 40 plus 160, 200. So what is my velocity after? It's going to be 800 divided 200, which is 4 meters per second.
Okay, sure.
Okay? Okay, let's try another one. So what is the momentum of the pig? Each
8,000.
Yep, 8,000, 800 times 10, and then the other dude?
Negative 6,000.
Okay, negative 6,000. And what is the speed of the two together after the impact?
Is it 1?
Yep, it's 1. So the total before is 800 plus negative 8,000 plus negative 6,000, which is 2,000. And then I divide by the total mass, which is 800 plus 1,002, which is 2,000 as well. So 2,000 divided 2,000 gives me 1. Okay, Zinia, can you understand?
Yes, sir.
Okay. Okay. Try the next one. Okay, now the trick here is they don't stick. That's the situation now. So just now they stuck together, but now they're not sticking together. So let's look at the momentum of the skater before impact. The elephant,
105,000.
okay. And how about the penguin?
Question negative 1,000.
Yep. So we've got the momentum of each of them. Okay, and then now the question says the speed, what is the speed of the elephant if the penguin goes 50 meters per second after the impact? So now they're come together and the penguin is going to move 50 meters per second after the impact. So what is the speed of the elephant? Now they don't stick together, which means that you cannot add their mass together because they're not sticking together. They're going to move separately. So what is the speed of the elephant?
Is it 17.5?
17.5. Nope. You should get 27.8. Remember, the key here is because they're not sticking, my momentum before collision, when I add them together, is equal to the momentum after collision, but I cannot add the masses together because they're not going to stick together, so they're not going to have an addition of masses moving together. So I have to calculate them separately. So you come up with you can come up with an equation, and your unknown will be the speed of elephant. Anyone has any idea?
Except for the equation.
Yeah,
Uh,
the equation.
I don't understand.
Okay, so I have, let's see, momentum before collision is equals to momentum after collision. That's the concept. Okay. So now we see that momentum before collision is, just now what we saw, 105,000 plus with the penguin is negative 1800. So I'm just going to straight away put negative 1800. And that is equals to, okay, now remember I said they don't stick. So they're going to have, because they're going to not stick, they're going to have different masses, of course, and they're going to have different speed, which means they're going to have different momentum as well. So you calculate the momentum separately. So the elephant has a mass of 3500 and the speed is x because that's what we want to find. Added with the mass of the penguin with the velocity of 50 because it says the penguin goes 50 meters per second after the collision. Okay, and then now you can solve it. 105,000 minus 1800 is 103,200. And then that is equals to 3500x plus with 6,000. Then I just shift things around. So I bring 6,000 to the other side. I should get 97200. And that is equals to 3500x. And to solve for x, you take 97200 divided by 3,500, and you should get,
27.8.
yeah, 27.8. Okay, and everyone can?
Yeah, sure.
Sure.
Yeah, so just remember, after collision, if they don't stick, then you don't add their masses together, because they are still separate entities. So you calculate their momentum separately as usual, and then you can find out whatever you need to find out. Okay, any questions so far?
No, sure.
No? Okay, so that is my conservation of momentum. Okay, just give me a second. Okay. So that is for momentum. And then we have, the other one was, on sound. Okay. So for sound, just give me a moment. Okay, for sound, there are a couple of things that we need to look at. So we have, we know that sound is produced by vibration of air particles. Okay, so that produces the sound. And then we look at speed of sound. So speed of sound is basically, we're looking at speed equals to distance over time. Okay. And then, can you all see my slides?
No, sure.
Can you all see it? No, okay.
Sure.
Okay, now can you see?
Yeah, sure.
Okay.
Yeah.
So we have the basic things, wavelength, distance between the crest and the crest, or the trough and the trough. And then we have amplitude, and then we have frequency. Higher frequency is the same as higher pitch. Okay, low frequency is low pitch. So this part here is a low frequency. And then when the frequency is higher, it also equates to higher pitch of sound. Okay, and then we look at, okay, let's see, what else can we look at? Okay, when we're looking at amplitude, that also denotes the loudness of the sound. Higher amplitude just means louder sound. Okay. Sounds that are too high to hear is known as ultrasound, and if it's too low, it's known as infrasound. Okay, these are just some things to remember. Okay, and then we have frequency, calculating frequency of a sound is 1 over T, where T is the period. Okay, see if I can get the formula on the screen. Okay, so frequency is 1 over the period, and then another formula is also velocity over wavelength, V over lambda, and the unit of frequency is hertz. That is another formula for frequency. Okay, 1 hertz, when we look at because frequency is 1 over T, 1 over the period, it basically means 1 hertz is equals to 1 vibration in 1 second. That's essentially what it means. Okay, and the T, like I said, is period, is basically the number of seconds for 1 vibration. So 1 vibration is basically 1 oscillation. So one up and 1 down is 1 vibration, 1 oscillation. So the number of seconds for 1 vibration, that is the period. And when I take 1 divided by the period, I get the frequency, because frequency is essentially number of vibrations per second. Okay, so that is for sound. Okay, anything else on sound you all want to know about?
No, sure.
No? Okay. Then we can look at the last one, which is half-life. Okay. So, okay, we're looking at atoms having the same element having the same number of protons. They can have different number of neutrons, and that's what we call isotopes. Okay, and if isotopes are radioactive, basically the nucleus is unstable. So when it's unstable, it's trying to become stable. So in the process of becoming stable, it emits particles or waves. Okay, and it doesn't come stable like straight away. Maybe after a few rounds of degenerating. So in that process, they emit radioactive particles, and this process is called decay, radioactive decay. It's a natural and random process. Okay, the activity of radioactive isotope is the number of atoms that decay per second. Okay, and then we see half-life. So when the decay happens, it happens at its own rate. Different elements, different particles, different radioactive substance will decay differently at their own pace. Okay, so when the time taken for the radioactive particle to become half of its origin of the value before, that is the half-life. Okay, so average time to halve the nuclei in a sample to decay, and then if it halves again, it's undergone a process, and that is another half-life, because there's another time taken for it to half from the previous amount. Okay, so for example, the half-life of iodine 131 is 8 days. Okay, so after 8 days, half the nuclei will have decayed. That's what it means. If the half-life is 2 days, that means after 2 days, it would have decayed by half. It would have been half lesser, half the amount. Okay. So we can do many calculations. For example, carbon-14 is 5,700 years, the half-life. So only after 5,700 years, it becomes half the amount. So if a fossil bone has a count of 25 and a piece of bone from a living body has a count of 200, how old is the fossil? So after one half-life, the count will be decreased by half. So from 200 becomes 100. And half-life is 5,700. So after the second life, the count will decrease by 50. And then after 50, and then it's 25. Okay, so it has undergone 3 half-lives. From 200 to 100, that's one. 100 to 50, that's another one. 50 to 25 is another one. So 3 half-lives. So one half-life is 5,700 years. So 3 half-lives will be 17,100 years. Okay, so that means the fossil is 17,100 years old. This is called carbon dating. Okay.
Okay, sure.
Okay. Some nuclei are more unstable, some are stable. They decay at a faster or slower rate, again, depending on the type of nuclei. Okay, so I have xenon-133, a radioactive isotope used for studying lung function. Its half-life is 5.2 days. Why does it make it suitable? Why do you think it is suitable to have a half-life of 5.2 days? Why? What will happen if the half-life is maybe 20 years?
So then, like, so the lungs will be full of like radioactive material.
Yeah, for a long period of time, correct. That's why the shorter the half-life, the, I guess, less harmful it is to the body if it's going to go into the body. Okay, uranium-235 used in nuclear reactors and nuclear weapons has a half-life of 710 million years. Okay, and of course it's going to be
Do you have
considered.
to remember all this radio isotope?
You don't have to remember the number, like the half-lives, no. You just have to understand the concept behind it and how to calculate if they ask you a question. But you don't have to remember all these numbers.
Sure.
Yes.
Does the half-life never reaches 0?
This is the half-life, which that means the time taken for it to decay. That means there's no, it decays straight away, is it?
No, sure. Like it always halves. What does it ever reach 0?
Yeah. So when the amount reaches to 0, that's when the radioactive substance is dead. And then it is safe. There are a lot of like places where for let's say there's a gun shoot or some bomb explosion. So for a certain period of time, that place or that area will be filled with radioactive substances, and then it will take a while for it to decay, but it does reach 0 over time. Then
Okay,
that
sure.
means the radioactive substance has died lah, so it's not active anymore. But yeah, it does reach 0. The only question is how long it takes lah.
Okay, sure.
Okay. Okay, so nuclear waste, especially when it takes a long time, the area where it has been contaminated by it will be affected. Okay. Okay, so that is all for half-life. Okay, anyone has any questions so far?
No, sure.
No? Okay, then if that is the case, then you all can take a quick break. And what time is it? Now it's 9:55. Come back at 10:05, and then we will do some questions from the past year paper. Okay?
Teacher.
Okay. Okay, I'll repeat that again. Define acceleration, rate of change of velocity. Or you can say change of velocity over time, divide time.
Yeah, so let me take my past year paper.
Okay. Or v minus u over t. Okay, quick question. How are y'all with your past year papers? How do y'all usually do it? Do y'all set a time? Do y'all still do y'all do the paper first and then mark it later, or do you look at the answers and try to study that way? How do y'all do it?
I just do it.
Ooh.
Okay,
Nice.
let me ask one by one. Okay, CK, how are you with your past year papers so far?
Sure, just good. Like I do as much as I can, and then the ones that I don't know, I just check the answers and try to get the same answer.
Okay. Cedric, oh sorry, before that, how are you with time? Do you time yourself when you do your past year paper, CK?
Sure, last time I didn't, but now I'm starting to time.
Okay. Okay, Cedric, how are you with your past year papers?
Same as CK. I try to do without the questions, but I pretty much complete the whole paper first.
Okay.
Some I don't answer, and then look at the answer. If I somehow know it, I just use the calculator or just try to understand it. But then if some answers, like some questions that I can't answer, that I just don't, then yeah, I can't.
Okay. Daman?
I just do it. I don't time myself.
Okay. Desiree? Okay. James?
Yeah, I generally just try and keep my time within the limit of the paper.
Okay.
For any, yeah.
And are you usually able to finish it?
Yeah, I can finish most of them, but there are a few here and there that I don't know how to do, which I'll leave and then come back to the answers later.
Okay. Desiree? Okay, still no response. Justin? Justin, how are you with your past year papers?
Same as Dama. I just do. I don't time myself.
Okay. And are you able to do, if let's say out of 100% of the paper, how much are you usually able to do? Or how much are you able to finish?
It depends.
Depends on.
Like just like staying at home at like no mood to do. Then like, sometimes I do halfway there. I suddenly doze off.
Okay, just make sure in exam time while you don't sleep off.
Yeah, I will.
Okay, Yonghong, how are you with past year papers? Okay, no response as well. Mushiga, how are you with past year papers so far?
Okay, it's the same as CK, but I just don't time myself.
Okay. Zinia?
Same as CK, but I'll try to time myself next time.
Okay. So basically, right, we will try to cover as much as we can in terms of past year papers on Zoom. What I would advise y'all is to start timing yourselves. Like paper 4 is 1 hour 15 minutes. So you want to get into the groove of trying to do the paper as quickly and as accurate as possible. Because yes, we want to be meticulous about what we're writing, but at the same time, if we're too meticulous at the start and a huge amount of time is taken towards just like trying to write properly and stuff like that, then we will miss out on a lot of questions. For example, 1 hour 15 minutes for altogether 11 questions. Okay, so 1 hour 15 minutes is 75 minutes. Divided by 11 questions, one whole question, which includes your A, B, C, 1, 2, should take you approximately 6.8 minutes. So slightly less than 7, not even 7 minutes yet. If we were to, and then that excludes, and that is not inclusive of you checking your paper or going back to the questions that you were not able to do. So you want to be able to try and do as much as you can within a short period of time, so that when you're done, you can go back to the questions that you were unsure of. And remember, you also have to check your work. Okay, so the thing with questions, if you have been doing your past year papers and we've been discussing, you would see that there is a pattern to the questions that they ask. Like the first question, a lot of the times it has to do with acceleration or speed or finding the area and all these kind of very, very simple questions. And usually they ask you questions based of the sequence of your topics in the textbook. Okay. Like the decays and everything, those comes at the end because that's towards the last chapter. And then light and sound is towards the middle. And then the starting is your forces and energy and stuff like that. So you can sort of gauge at which part of the paper, what types of questions they're going to ask. So you want to practice doing it quickly. Quickly, you got to do it accurately as well, but you must train your mind to be able to read quickly. And one very helpful thing is when you read, right? Because you're trying to read fast and finish it fast. You read quickly, highlight the keywords while you're reading it the first time itself. Highlight the keywords and then look for the question. Okay, what are they asking for? Then you don't have to go back to the paragraph and search for the keywords because you've already underlined it. So all these things are actually very, very important. It sounds very tedious, but it actually helps you to do your work faster because again, you only have 75 minutes to do your work. So I would advise you all to start timing yourselves. When you start it, you might be taking longer. You might be taking like 2 hours or 1 hour 45 minutes. Don't be discouraged. Just keep doing it. The more you do, the more you will get the hang of, okay, I only have 75 minutes. Okay, keep drilling that in your mind. So that will help you to do it fast. Another thing that you can do, which I learned when I was doing exams was, so I have 75 minutes, right? And I have 11 questions. So what I do is I tell myself, okay, let's say your exam starts at 9. Okay, from 9 to 9:06, because 6 minutes, right? I'm going to do question 1. The moment 6 minutes has passed by and I have not finished, okay, I stop and I go to the next question. And then after another 6 minutes, I go to the next question. And then I leave out, if I feel like the next question that I'm supposed to attempt I cannot do, I leave out first. So at least I have tried all 11 questions. Because the last thing you want to do is you do 8 questions and then the last 3 questions you did not even attempt at all. Because usually the questions, like for example number 4, A, B, you're usually able to do. It's not difficult. Maybe C1 or C2 might be a bit challenging, but usually the first 2 questions of each question is not difficult to do. So you want to be able to at least attempt all 11 questions. So what I usually used to do was, because again, struggling with time, I would tell myself, okay, for the next first 10 minutes, I'm going to try to do question 1. The moment 10 minutes is up, whether I finish, even if there's one more question, I move on to the second question first. I keep doing that so that I attempt all 11 questions. And then usually when I do that, I usually have extra time to go through the questions that I haven't done yet. But like I said, at least you have tried all 11 questions. So if that method works for you, you can try that. If the more you do, you're able to shorten, you're able to finish it in time, then do that. But please start timing yourself, okay? Because it's very, very, very important. Okay, because you don't want to lose a good amount of marks. If you lose marks because you don't know how to do, then that's fine. But if you lose marks because you didn't have time to do, but you actually knew how to do it, it will be very frustrating, because you'll be like, oh, I should have done it much faster or something, because you know how to do it. So keep those things in mind, so that you don't not do something that you knew how to do. Okay, so let's continue. Define acceleration, like I said before, rate of change of velocity, or change of velocity over time. And then speed time axis for the graph of motion of cars. So I have speed and time. The car starts from rest, from 0
Repeat
to
question 1 answer again.
Change of velocity over time.
Thank you.
Okay, I have the time given and I have the acceleration, the speed for each of it. So draw the graph using the space. Okay, you can use the space for calculation. So I have from 0 to 15, the car has a constant acceleration to a speed of 28. So from 0 to 15, so 15 is about here. So constant acceleration means my gradient is constant, which means I will have a linear graph from 0 up to 28. Okay, does anyone want to try drawing? You can draw on my screen.
I don't have the physical paper, but yeah.
Sorry?
I don't have the physical paper. I do it in the online. So
Oh yeah, that's fine. That's completely fine. But would anyone like to draw on my screen?
I try.
Can try. Justin, you gonna try? No, yes?
Yeah, I'm doing it.
Okay. There is another line feature that is for straight line. You can use that. Then you will be able to draw like straight lines.
To do the deceleration one also.
Your graph from 0 to 15 seconds, the car has a constant acceleration. So 15 seconds is here. And your graph should reach to 28 meter per second, which is up there, because the question says constant acceleration to a speed of 28. So from 0 to 28, 28 is somewhere here. So your line should be something like that, a bit more steeper. Yep. And then the next one says from 15 to 32, constant speed of 28. (15 to 32). Correct. And then it says deceleration of 2 meters per second until it comes to a rest.
That's when I don't know.
And that's from time 32 seconds. Constant deceleration of 2 meters per second until it comes to a rest. Okay, anyone else wants to try? So we have acceleration, it's decelerating. So from the previous formula, acceleration is rate of change of velocity or change of velocity over time, right? So we have acceleration, A is equals to V minus U over T. Okay. So my V is final velocity and U is my initial velocity. So we're looking at just from 32 seconds onwards. From 32 seconds, it's going to start decelerating. Okay, so I don't know what my final, my final velocity is going to be 0 because it's going to come to a rest. So my V is 0 minus my U, I'm starting off with 28 because only we're looking at this portion of the graph only. So my initial velocity will be 28, my final velocity will be 0 because rest. Okay, and I don't know what my time is, but I know my acceleration is 2, or in this case, my deceleration. So 2 is equals to 0 minus 28 over the time, which is what I don't know. So to calculate for time, I take 28 divide by 2, which is 14 seconds. So it takes 14 seconds for the car to decelerate. So from 32, it's going to go 14 seconds later, which is 46. So it's going to decelerate until it reaches 46. Okay. So I would draw a line like this. It's going to go up to 46 like that. Okay, can I understand?
Yes, sure.
Yeah? Okay. So you calculate the time and then you will be able to, so it's the time is 14 seconds. 32 to 14 will, 32 plus 14 is 46. So then I just draw a decelerating line down there to up until it reaches 46 seconds. Okay. Let's move on. Okay. So here is where you can use the space for calculation. Okay. From time 15 to time 32, the path of the car is part of a circle. Okay. The part of the car is part of a circle. The path of it. So it's part of a circle. For this motion, state the direction of the resultant force on the car. So from 15 to 32, that's when the car is at constant speed. It says that the path that the car is taking is part of a circle. So because it's part of the circle, the direction of the resultant force on the car will be towards the center of the circle. Okay, so inwards towards the center of the circle. And what happens to the velocity of the car? The velocity is changing its direction. That's why the speed is constant. So the velocity helps with the changing of the direction of the car because it's going in a circle. So it's going in a circle, the wheel, right, is actually constantly changing, moving to the right or to the left. It's just that the velocity helps. It seems like we are not changing the speed of the car, but what actually is the velocity helps to change the direction of the car. That's why it moves at constant speed. So the direction of the resultant force is towards the center of the circle. And what happens to the velocity? The velocity is changing the direction of the car. So it's continuously changing the direction because it's going in circles. So you have to constantly turn. when you're going on a roundabout, you're constantly changing the direction of the wheel. What helps you to change the direction of the wheel is the velocity of the car. And the direction is continuously changing because you're going around a circle. So it's actually constantly changing direction. It's turning to the right a little bit more, a little bit more, a little bit more. So it's constantly changing direction. So the velocity is the one helping to continuously change the direction of the car. All okay so far?
Yes, sure.
Yes.
Yep. Okay, let's look at number 2. A force is used to move an object from the Earth's surface to a greater height. Why the gravitational potential energy of the object increases? Why does it increase when it goes to a greater height away from the Earth's surface?
Because gravitational potential energy is force times the distance that the object is, like the height of the object.
Correct.
And the height is increasing gradually.
Correct. So the height is increasing, and we're looking at GPE is equals to the force times the distance that the height the object is rising up. So that is why the GPE of the object will increase, because the height is increasing. Okay. Okay, I have a train moving up towards the top of a mountain. The train transports 80 passengers, each of average mass 65, through a vertical height of 1600 meter. Okay, so I have, let me just put that. So I have the height, (1600). Okay. So calculate the increase in the total gravitational potential energy of the passengers. So you can use the formula of mgh. Okay, mass is in this case 65 kg times 80, because 65 kg is average of one person and I have 80 passengers, so 65 times 80 for the mass, times the gravitational potential energy. Here in this case they didn't write what it is, you can take it as 10, 9.8 or 10, and then the height is 1600 meter. So I just times all of that together. What do I get?
You take 5200 times 1600 times 10.
80 times 65 times 10 times 1600.
So
What do
then
I
you
get?
get 8.3 times 10 to the power of 7.
Yep. So you should get approximately 8.32 times 10 to the power of 7, and your unit is joule, because energy.
80 times 65 times 10.
Yeah. Times 1600. Okay, let's look at the next one. The engine of the train has a power of 1500 kilowatt. The time taken to reach the top of the mountain is 30 minutes. Calculate the efficiency of the engine in raising the 80 passengers 1600 meter to the top of the mountain. Okay, so there are a couple of ways that we can do that. So who wants to try first? I'm looking for efficiency. I'm given the power and I'm given the time. So when I'm given power and time, how do I calculate for efficiency?
Output over input.
Okay, so we know that efficiency is always output over input. And then I times 100%. Okay, so now I have power is 1500 kilowatt. And then I have my time, which is 30 minutes. Okay, so I can do work equals to power times time. So I take work output over work input. So work done is equals to power times time. Power here is 1500. Okay, I need to change the kilowatt to watt. Okay,
So
so I
does
have
it
to
mean you times 1,000?
times, yes, I times 1,000. So 1500 times 1,000, and then the minute I change to seconds. So I times 60. So 1500 times 1,000 times 30 times 60. Okay, I should get 2.7 times 10 to the power of 9 joule. Okay, everyone okay so far? All following?
Yeah, sure.
Gotcha.
Yeah. Okay,
Yes,
so that
sure.
is my work input. Okay, so now I have, let's see, efficiency. I have from previously, I have, what did I get from the previous question?
Is it 8.32 times 10 to the power of 7?
Yes, correct. So from previously, I got 8.3 times 10 to the power of 7. That is the increase in total gravitational potential energy. Okay, and then I divide that by what I just calculated, which is 2.7 times 10 to the power of 9. And then I times 100%, and I should get 3.1%. Okay, so I take the previous one, the GPE, divided by what I just calculated, which is 2.7 times 10 to the power of 9, and then I times 100%. Because the GPE is the work done, because that is the increase in the gravitational potential energy. That means the increase in the work that was done.
Check it 0.0308.
Then you have to times 100%, because efficiency you have to times 100%.
3.08.
Okay, so my increase divided by my input, which is 2.7 times 10 to the power of 9, and then I times 100%, I should get 3.1%. Okay, let's look at the next one. Complete the statement by writing the blank spaces. The moment of a force about a pivot is equal to what multiplied by what?
Force times perpendicular distance to the pivot.
Correct. So moment about a pivot is equal to force multiplied by perpendicular distance from pivot. Okay, I have a
Repeat the
horizontal.
answer for 3A.
The moment of force about a pivot is equal to force multiplied by its perpendicular distance from the pivot. Okay, I have a horizontal rod of length 2.4, weight 160 Newton. The weight of the rod acts as its center. The rod is suspended by two vertical ropes X and Y. The tension is 80 on both. State the name on each. State the name given to the point at which the weight of the rod acts. So when the weight of the rod is the weight of something is acting on something, what is it? What is that point called?
The center of mass.
Yeah, center of mass. Calculate the mass of the rod. What is the mass of the rod? I have the weight is 160. So what would the mass be? How do I calculate the mass?
16 kg.
Yeah, so I take 160, which is the weight, divided by 10. So it's 16 kg.
Divide by 10.
Yes.
Why? So why divide by 10?
Because this is in weight, Newton. To go to kg, to convert to kg, you divide by 10.
Oh, okay.
From mass, you want to go to weight, you times 10. Okay, the rod is in equilibrium. Using data from figure 3.1, explain why. Why is the rod in equilibrium?
Sure, there's no resultant force acting on the rod.
Yeah.
Since
So if
both
something is correct,
it out. Yeah.
so there's no resultant force.
No turning effect.
Yes, no turning effect, because there is no resultant force. The upward force and the downward force are equal to each other. So the rod is in equilibrium, so it's not moving.
Yes.
Okay. So there are 4 marks here. So you want to talk about there's no resultant force. Okay. You want to talk about how 80 Newton at the top and 80 Newton at the top here, when I add them together, is equal to 160 at the bottom. That's the second one, why it is equilibrium. Okay, and then I'm sure we also talked about this last week. I think there was a similar question last week or the week before. When we're looking at moment, we have anti-clockwise and clockwise movement. In this case, my clockwise moment and my anti-clockwise moment are equal to each other. Okay, so if this is my center, this being my pivot, my force 80 Newton and my distance, perpendicular distance to the pivot, which is 1.2, half of 2.4, 80 times 1.2 will be equal to the other side, 80 times 1.2. So because they are both equal, that means my anti-clockwise moment and my clockwise moment is equal to this. It is equal. So that is why my rod is equilibrium. So 4 things, 4 marks. So you want to talk about no resultant force. You want to talk about how 80 and 80 at the top is equal to 160 at the bottom. You want to talk about my clockwise moment and anti-clockwise moment are equal. And then you denote it as 80 times 1.2 on the left equals 80 times 1.2 on the right. So anti-clockwise and clockwise moments are going to be the same. So the rod is in equilibrium. Okay, any questions so far?
No, Chair.
Okay, figure 4.1 shows a cold plastic spoon that has been placed in hot liquid in a cup. So the plastic spoon is cold, the liquid is hot. Describe in terms of molecules why the temperature of the whole of the spoon increases. Why does the temperature of the whole spoon increase in terms of molecules?
Sure, the liquid molecules are colliding with the spoon's solid molecules and transferring the heat energy.
Okay. correct? So I have, when the spoon is placed into the hot liquid, the molecules of the hot liquid will start colliding with the spoon surface. And when they collide, they transfer energy, they transfer heat to the spoon. Okay, so this will increase the temperature of the spoon, because when they transfer energy to the particles on the spoon, the particles on the spoon now start vibrating because they have received heat. So this will, when they vibrate, they will increase the temperature of the spoon. Okay, now the plastic spoon replaced by metal spoon. What is an additional process by which the temperature of the spoon will increase? Now it's not plastic, now it's metal. So what is involved here when it is metal? We have molecules from the liquid. Now there is something additional because it's a metal spoon. Now we have electrons. So now the molecules of the hot liquid will transfer the energy, the heat energy, to the electrons in the spoon. And then these electrons will move through the metal, and this will increase the temperature of the spoon. Okay, next one, cup containing 150 grams of liquid, specific heat capacity 4.2. Cold spoon placed in hot liquid, temperature decreases from 80 to 56. Calculate the loss of thermal energy from the liquid. Okay, let me call someone. Desiree, how do you do C? I want to talk about loss of thermal energy, okay?
Take 150 and then times it with 4.2.
Okay, why 150?
Because it is
Why are we taking 150?
I'm not sure, I just took it and just times it.
Okay, we're looking at specific heat capacity. What formula do we use?
Is it mass times change in temperature?
Yep, so I have Q equals to MC theta. So I have mass is 150. And then C is the specific heat capacity. In this case will be 4.2. And what is my change in temperature?
24.
Yep, 24. So I times that all together. What do I get?
So 15,000 joules.
150 times 4.2 times 24. Oh, just a second. You should get 15,000 joules.
So, but I got
15,120.
Yeah.
Yeah. Correct. 15,120. Yeah. Okay.
Okay, Joe.
So now I have 15,120 joule. That will be my that will be MC theta. Yeah, correct. So now they're asking for just a moment. The cup contains 150 grams of liquid, 4.2. When the cold spoon is placed into the hot liquid, the temperature of the liquid decreases from 80 to 56. So it has decreased by 24 degrees Celsius. They're asking to calculate the loss of thermal energy. So how do I get loss of thermal energy? How do I get loss of thermal energy, guys?
So mass times specific heat capacity, then times the change in temperature.
So my mass is 150. My specific heat capacity is 4.2. My change in temperature is
24.
24. So I have 15120 joule. That means the answer here is wrong. The answer in the answer scheme says 15,000. It should be 15,120 joule.
Yeah, usually the marking scheme, they just try to round it up.
Yeah, but you should put 15,120 joule. Okay.
Okay, sure.
Okay. I want to go to, there are a few more questions. I will upload the marking scheme later, but there are some questions I just want to look at before we finish off. Okay, let's look at this. Number 8, the lamp of a car headlight rated at 12 volt, 50 watt. Calculate the current in the lamp when operating normally. So I use P equals to I times V. So the current will be P over V. My P is 50 and my voltage is 12. So I should get, what do you all get for current?
4.167.
Yep, 4.167 amperes. So make sure you put the A there. Okay, next, a car driven at night, the total charge that passes through the 12 volt battery is 270 kilo coulomb. Calculate the electrical energy transferred. What formula do I use for energy transferred? Given the charge and the volt. I use my charge times the volt. So 270, I times by 1000 first to bring it to coulomb, and then I times with my voltage, which is 12. So I should get 3.24 times 10 to the power of 6 joule. Okay, everyone got that? Anyone
Yes.
confused?
No, Chair.
No? Okay. The fuel used by a car provides 3.6 times 10 to the power of joule per cm cube. Calculate the volume of fuel used to provide the energy calculated in B1. So the energy calculated was 3.24 times 10 to the power of 6. The fuel used by the car provides 3.6 times 10 to the power of 4 joule. So what is the volume of fuel used to provide the energy calculated previously? So I just take the energy that I've calculated from before. I divide it by 3.6 and I will get 3.6 times 10 to the power of 4 and I'll get the volume of the fuel used. So 3.24 times 10 to the power of 6 divided by 3.6 times 10 to the power of 4. And I should get the volume.
So the volume is 89.
Yes. You should get, let me just double check, calculate 3.24 times 10 to the power of 6 divided by 3.6 times 10 to the power of 4. If you use 3.24, you should get 90 cm cube. If you use 3.2, then you probably get 89. All okay?
Yes, sure.
Okay, let's look at this one. I have a transformer. Primary coil is 800 turns, input 240 volt. Secondary coil has an output volt of 12. What is the number of turns in secondary coil? Sorry?
400.
Yep, you should get 400. So voltage in primary divide voltage in secondary is equals to number of turns in primary over number of turns in secondary. You just put the values in and you should get 400. Everyone got that?
Yes, sure.
Yes, sure.
Okay. Okay, let's look at this. Okay, C1. Look at the numbers, the decays. So what would be the type of radiation emitted for the first one?
Should gamma radiation?
No, not quite. From
Alpha.
95 going to 93. This should be alpha particle. How about the second one?
Beta.
Beta.
15 going to 16. Okay. Gamma, remember, we cannot see. It is like extra energy being released, extra radiation being released. So it will not affect the numbers of the protons and neutrons.
Oh, okay,
Between
sure.
alpha and beta. Beta, the number will increase. Alpha, the number will decrease. That's the easiest way to remember that lah.
Okay, sure.
Okay. Okay. I will upload the answers on Edmodo. You all can check. If you all have any questions, you can ask me. I will upload the questions for the answers for paper 2 as well. Okay. And then if you have any, I think paper 2, I've already uploaded the answers, in fact. Do you all have any questions on paper 2?
No,
Anything
sure.
you're unsure of?
Yeah.
Okay, if you have no questions, Rin, then we can end here for today. And then we'll continue next week. Okay?
Sure.
Okay.
Thank you, sir.
Thank you.
Thank you, Joe.
Thank you.
Thank you, teacher.
Thank you, Chair.
Thank you.